Welcome to our first chapter, Speaking Mathematically. We're going to talk about how to understand the language of mathematics, how to communicate, and so forth. That is where we are going to start. So, for instance, we're going to first talk about what are variables. Now, a variable is pretty much just a placeholder. You know it often as X, but the truth is we can use anything. N, square, you name it. For those who are computer scientists, it's the same kind of general idea. It's just something to take advantage of something to hold a place while we talk about it. So for instance, let's consider, is there a number with the following property? Doubling it and adding 3 gives the same result as squaring it. Well, we could take that and we can write it as doubling a number is 2 times that number, plus 3 equals x squared, the square of that number. So this sentence is the exact same thing as that long situation on there. And we often really like when we have a nice, clear sentence to attack and understand. The advantage of using this is that it actually allows us to have a temporary name that we can call back. Just like in computers, when you punch something in, you do an I and then iterate through an I is an index, you're iterating through an array or something. It's the same idea. Now, we could also just use a box. I mentioned this before. Now, it's kind of boring to draw a box. I personally have done smiley faces and other things like that just to have some fun. So in a sense, we're just doing something to fill a spot and understand. And last but not least, talking about variables one more time is, let's just look at this in another sentence. No matter what number is chosen, if it is greater than 2, then its square is greater than 4. Now, we can again say it can just become n, being an arbitrary number. Again, I can use the number n and so forth. So I want you to try this. Now, this is a good way to practice how we're going to do our videos. I want you to pause the video and see if you can rewrite both of these sentences using some kind of variable. So the first one is, are there numbers with a property that the sum of their squares equals a square of their sums? And the second one is, given any real number, its square is negative. All right, try that. All right, hopefully you paused it. Not, go do it now. If you already did pause it, now you're unpaused, let's move on. So the first one, you can write that as a squared plus b squared equals a plus b quantity squared. Now, the really nice part about this is the fact that it lets us see it differently. And we can still use we still have to use the words. Are there numbers a and b with said property? Or are there numbers with that property? Do there exist numbers such that that's true? So notice we're still using words, but the variables are just used to condense the part that talks about the sum and the squares and the equal. But we still use words. Don't stop using words. That's kind of important in this class. Also, for any real number r squared is non-negative. So instead of saying its square is not, or because remember we said its square is non-negative. For those who don't know, non-negative simply means it's bigger than or equal to 0. It's not negative. Well, 0 is not negative, nor is any positive number. So for any real number r, or for every real number r, still is true. And we'll get back to a little more about the any and every and so forth. This actually gets into what's known as predicate logic, but we'll talk about it more. Now, there's also some important kinds of mathematical statements that we need to talk about. Namely, we need to talk about what are called universal statements, like a certain property is true for all things. All positive numbers are greater than 0. Okay, that's true. And the other one is conditional. If, then. Okay. So one is an all statement, the other is an if-then statement. And we also have existential, meaning there is some prime number that is even. All we need is one number for that to be true. So universal is everything has to be true. Conditional, if the if part's are true, the then part has to be true. And existential, there's something with this property. At least one. There could be a million. I don't care. I just need at least one. So let's talk about universal. So a universal statement is something that universal conditional is like for every animal A, that's the universal part. If A is a dog, then A is a mammal. Okay. One of the most important facts about these is they can be rewritten in many ways to make it purely universal or purely conditional, but usually we kind of do it. For example, I could write it as if A is a dog, then A is a mammal. That kind of implies that for all dogs, if A is a dog, in other words, for every dog A is a mammal, or all dogs are mammals. This has no if then, but it is actually still a universal. So how we manipulate things is actually kind of important because they send the same message, but are communicated in different ways. Try this for just pause the video and try this one. So how would you fill in the blanks for this one, starting with for every real number x, if x is non-zero, then x squared is positive. Now, how would you finish the rest of the sentences? Try it. All right. So if you did that, the first one, if it is a real number is non-zero, then its square is positive. We can say that. The second one, if every non-zero real number x squared is positive. If x is a non-zero real number, then x squared is positive. We can continue on the next one being it is positive. And the last one, they have positive squares. So there are lots of ways to talk about that. All right, let's talk about existential statements. Now, existential, remember, means there exists something. So universal existential is for every real number has an additive inverse. Why is this universal? Because I mentioned every real number. I also said it has an additive inverse. Now, we haven't talked about what is an additive inverse yet. An additive inverse is really just something I add it to makes it go zero. But I'm saying there exists an inverse. I'm not saying what it is. I'm just saying there exists. So that's the existential part. All right, here's another one. So sometimes it depends on what is the actual thing. So for all real numbers of additive inverse, I could also say for every real number r, there's an additive inverse of r. I'm adding that little detail just because sometimes it's really important, depending on the quality or the property, or it could even get even crazier. For every real number r, there is a real number. So there's the for all part, and there is the existential part, s, such that s is the additive inverse for r. You see how this works? All right, one of the most important reasons we do this is the ability to refer to quantities ambiguously without a lengthy mathematical argument. We don't like to say things really, really long. We want to be concise and clear. We do want to write things and use words, but we don't want like 5 paragraphs when one line will do. So I want you to think for a second. Our statement is every pot has a lid. How can you modify finish these 3 sentences so that they still convey the message that every pot has a lid? Pause and try. All right, so if you did this, all pots have lids. For every pot P, there is a lid for P, and for every pot P, there's a lid such that L is a lid, the lid for P. So the second one, I'm picking out a lid that fits P. I'm sorry, the third one. Second one, I'm saying if there's a pot, then it has a lid. And the top one just says all pots have lids. All right. Now, we also have existential universal. Notice the difference is I mixed the order up. So in this one, there is a positive number that is less or equal to every. So I start with the there is, that means there's some, and I end with the for every or all. So there is a positive number that's less than or equal to every positive integer. Okay, that's true because the number 1 is a positive integer and it satisfies the property of being less than or equal to every other positive integer. Now, we can also come back and rewrite this a couple other ways. We can say there is a positive integer m that is less than or equal to every positive integer. Now, notice I'm adding an m into the situation. There is a positive integer m such that for every positive integer, it is greater than or equal to m. Notice I switched it. Instead of saying less than, greater than, okay? So I can look at things from different sides. There's a positive integer n with a property that every positive integer n, and now we wrote it mathematically, the inequality that we keep referring to, m less than or equal to n. All right. So I'm going to go ahead and skip this rewriting exercise. You can pause the video and look at it if you want. And then if you want, here are the quick answers. But here's the really, really big part of this. If it is conditional, if there is an if then. It is universal if there's a for every or for all. Existential is there is, there exists, etc. So we have to use these statements over and over and over again to get comfortable with them. All right. Last example of something maybe you saw in calculus is the limit of a sub n is actually there was a for every positive integer, positive real number epsilon, there is an integer n such that for every n little n, if n is bigger than n, then negative epsilon is less than a sub n minus big L is less than epsilon. That's the idea of a sequence of numbers approaching a value as we go to infinity. Perhaps you actually saw this. If you did not, that's okay. But it's just an example of for every, there is a universal. There is existential. For every, it is universal. And if then, conditional. So get to know these. Those are key things throughout logic and everything else in math that we are going to utilize. Good luck.